The universe, that vast and mysterious expanse that has captivated human imagination for millennia, is not just expanding, it's accelerating. This mind-boggling discovery has sent scientists scrambling to understand what this means for the ultimate fate of everything we know. Is the universe destined to expand forever in a big freeze? Or will it collapse in a big crunch? Or perhaps, in a twist straight out of a sci-fi novel, is it headed for a big rip? Each of these theories carries profound implications, not just for the cosmos, but for our very understanding of existence. Stick around, because we're about to dive into the cutting-edge science that's reshaping our view of the universe and our place within it. Historical perspectives on the universe. Throughout history, humanity's understanding of the universe has evolved dramatically, shaped by cultural, philosophical, and scientific developments. Ancient civilizations often viewed the universe as a finite, Earth-centered system. For instance, the ancient Greeks proposed the geocentric model, with the Earth at the center and celestial bodies moving in perfect circles around it. This perspective dominated Western thought for centuries, influencing everything from daily life to religious beliefs. Meanwhile, other cultures, like the ancient Chinese, developed their own complex cosmologies, often incorporating celestial observations into their understanding of the universe's structure and fate. The Middle Ages saw a blend of ancient Greek ideas with religious doctrines, particularly in Europe. The universe was often depicted as a hierarchical structure, with Earth at the bottom and heaven at the top. This view was challenged during the Renaissance and the scientific revolution. Nicholas Copernicus proposed the heliocentric model, placing the sun at the center of the universe. This shift was monumental, as it laid the groundwork for modern astronomy. Galileo's telescopic observations further supported the heliocentric model, leading to a fundamental change in how people perceive the universe's shape and their place within it. In the 20th century, the discovery of the expanding universe by Edwin Hubble revolutionized cosmology. Hubble's observations of redshifts in the light from distant galaxies suggested that the universe is not static but is expanding. This led to the development of the Big Bang theory, which posits that the universe began as a hot, dense point nearly 13.8 billion years ago and has been expanding ever since. This theory has profound implications for the shape and fate of the universe. If the expansion continues indefinitely, the universe may end in a big freeze, where galaxies drift apart and stars burn out. Alternatively, if the expansion slows and reverses due to gravity, the universe could collapse in a big crunch. Comparing these historical perspectives reveals a fascinating evolution of thought. Early models were often tied to religious and philosophical beliefs, while modern theories are grounded in empirical evidence and mathematical models. The implications of these theories are vast. For instance, the Big Bang theory suggests that the universe has a finite age and will continue to evolve. This challenges traditional notions of eternity and infinity. Moreover, the expanding universe model has led to the concept of dark energy, a mysterious force driving the acceleration of the universe's expansion. Understanding the shape and fate of the universe is not just an academic exercise. It shapes our understanding of existence itself. The cosmological principle. The universe, on the largest scales, appears remarkably uniform. This observation is the foundation of the cosmological principle, which states that the universe is homogeneous and isotropic. Homogeneous means that the universe looks the same in all places, while isotropic means it looks the same in all directions. This principle is crucial for our understanding of the universe's shape and fate. It allows cosmologists to apply the same physical laws and models universally, simplifying the complex task of studying the cosmos. However, the cosmological principle is not without its controversies. Some theories, like the fractal universe model, challenge the idea of homogeneity. These models suggest that matter is distributed in a fractal pattern, with structures repeating at various scales. If true, this could significantly alter our understanding of the universe's shape and evolution. Yet, current observations, such as the cosmic microwave background radiation, support the cosmological principle. These observations show that the universe is remarkably uniform on large scales, with only minor fluctuations. The implications of the cosmological principle are profound. It underpins the standard model of cosmology, which describes the universe's origin, evolution, and ultimate fate. For instance, the principle allows us to calculate the universe's age, composition, and expansion rate. It also informs our understanding of dark matter and dark energy, which are thought to make up approximately 95% of the universe's total energy density. Without the cosmological principle, these calculations and predictions would be far more challenging, if not impossible. Critics argue that the cosmological principle might be an oversimplification. They point to large-scale structures, like galaxy filaments and voids, which suggest that the universe is not perfectly uniform. Moreover, some theories, like the multiverse hypothesis, propose that our universe is just one of many, each with its own unique properties. If true, this could render the cosmological principle irrelevant, as it would only apply to our specific universe. Despite these challenges, the cosmological principle remains a cornerstone of modern cosmology, guiding our exploration of the universe's shape and fate. Observational evidence in cosmology. The cosmos, with its vast expanse and mysterious nature, has always intrigued humanity. Observational evidence in cosmology serves as the backbone for our understanding of the universe's shape and fate. Cosmologists rely on a variety of observational tools and techniques to gather data about the cosmos. These include telescopes that detect different wavelengths of light, such as visible, radio, and tinth rays, as well as other detectors that sense cosmic microwave background radiation, gravitational waves, and neutrinos. Each of these tools provides a unique perspective, contributing to a more comprehensive understanding of the universe's structure and evolution. One of the most significant observational evidences comes from the cosmic microwave background, CMB, radiation. This faint glow, detected in all directions, is the remnant heat from the Big Bang. The CMB provides a snapshot of the universe when it was just 380 years old. By studying the tiny fluctuations in the CMB, scientists can infer the density and distribution of matter and energy in the early universe. These observations support the inflationary theory, which suggests that the universe underwent a rapid expansion in its earliest moments. This rapid expansion would explain why the universe appears to be uniform and flat on large scales, a property that has significant implications for its ultimate fate. Another crucial piece of observational evidence is the accelerated expansion of the universe, discovered through observations of distant supernovae. These exploding stars serve as standard candles, allowing astronomers to measure vast cosmic distances. By comparing the expected brightness of these supernovae with their observed brightness, scientists found that the universe's expansion is speeding up. This acceleration is attributed to dark energy, a mysterious force that counteracts gravity. The nature of dark energy remains one of the biggest mysteries in cosmology, with different theories proposing it could be a property of space itself or a new type of dynamic field. The fate of the universe hinges on the nature of dark energy. If it continues to dominate, the universe may expand forever, leading to a big freeze, where galaxies drift apart and stars burn out. Gravitational lensing also provides valuable insights into the universe's structure and fate. This phenomenon occurs when massive objects, like galaxy clusters, bend the path of light from objects behind them. By studying these distortions, astronomers can map the distribution of dark matter, which does not emit or absorb light but exerts a gravitational pull. These maps reveal a web-like structure of dark matter, influencing the formation and evolution of galaxies. The large-scale structure of the universe, as revealed by gravitational lensing, supports the idea of a flat universe, consistent with the inflationary theory. However, the exact shape of the universe remains an open question, with ongoing observations aiming to detect any slight curvature that could indicate a closed or open universe. The Hubble Law and expanding universe. The universe, in its vast expanse, has long been a subject of fascination and inquiry. One of the most profound discoveries in cosmology is the realization that the universe is expanding. This expansion is described by the Hubble Law, a relationship between the distance to a galaxy and its recessional velocity. The law is named after Edwin Hubble, whose observations in the early 20th century provided the first evidence for an expanding universe. The The Hubble law states that the farther away a galaxy is, the faster it moves away from us. This is often expressed as v equals hd, where v is the recessional velocity, d is the distance to the galaxy, and h is the Hubble constant, a measure of the rate of expansion. The implications of the Hubble law are far-reaching. If the universe is expanding, it suggests that it had a beginning, a concept that aligns with the Big Bang theory. This theory posits that the universe began as a hot, dense point nearly 13.8 billion years ago and has been expanding and cooling ever since. The Hubble law provides a way to estimate the age of the universe, although this estimate can be refined with more precise measurements of the Hubble constant. Different methods of measuring age, such as using type I supernovae or the cosmic microwave background, can yield slightly different values, leading to ongoing research and debate. The shape and fate of the universe are closely tied to its expansion. The Hubble law and the observed acceleration of this expansion, attributed to dark energy, suggests several possible scenarios for the universe's future. One possibility is that the universe will continue to expand indefinitely, leading to a big freeze, where galaxies become isolated islands in an ever-cold, ever-expanding cosmos. Another scenario is a big rip, where the expansion becomes so rapid that it tears apart galaxies, stars, and even atoms. Conversely, if the density of the universe is sufficient, it might eventually halt its expansion and begin to contract, leading to a big crunch. However, current observations favor an open or flat universe, where expansion continues forever. The Hubble law also plays a crucial role in understanding the large-scale structure of the universe. By mapping the recessional velocities of galaxies, astronomers can create a three-dimensional picture of the cosmos. This has revealed a web-like structure, with galaxies clustering along filaments and sheets, and vast voids in between. The Hubble law helps to calibrate these maps, providing a sense of scale and distance. Moreover, it allows astronomers to study the distribution of dark matter, which exerts a gravitational influence on visible matter and shapes the large-scale structure. The interplay between the Hubble law, dark matter, and dark energy continues to be a rich area of research, offering insights into the fundamental nature of the universe. The cosmic microwave background. The universe, in its vast expanse, has always been a subject of fascination and inquiry. One of the most significant discoveries in cosmology is the cosmic microwave background, CMB. This faint radiation, permeating the entire universe, is a remnant from the early stages of the cosmos, roughly 380 years after the Big Bang. It provides a snapshot of the universe when it was still in its infancy, offering crucial insights into its shape and ultimate fate. The CMB is remarkably uniform, with tiny fluctuations that hold immense information. These fluctuations, detected by sophisticated instruments like the Planck satellite, are the seeds from which galaxies and other cosmic structures eventually formed. The uniformity of the CMB supports the inflationary theory, which posits that the universe underwent a rapid expansion in its earliest moments. This theory helps explain why the universe appears so homogeneous on large scales. However, alternative theories, such as the ekpyrotic model, suggest that the universe's uniformity could result from a collision between higher-dimensional branes. These competing theories have different implications for the shape and fate of the universe. If the universe is flat, as suggested by the CMB data, it will expand forever, eventually leading to a big freeze, where all stars burn out, and the universe becomes increasingly cold and dark. On the other hand, if the universe is closed, it will eventually stop expanding and collapse back into a big crunch. The CMB data, combined with observations of dark energy, strongly favor a flat or slightly open universe. This has profound implications for the ultimate fate of the cosmos, suggesting that the universe will continue to expand indefinitely, albeit at an accelerating rate due to dark energy. The study of the CMB also sheds light on the composition of the universe. The precise measurements of the CMB fluctuations reveal the relative abundances of ordinary matter, and dark energy. These components play crucial roles in shaping the universe's structure and evolution. For instance, dark matter's gravitational pull influences the formation of galaxies and galaxy clusters, while dark energy's repulsive nature drives the accelerated expansion of the universe. Understanding these components is essential for predicting the universe's long-term fate and unraveling the mysteries of its fundamental nature. Large-scale structure of the universe. The universe, on a large scale, is a complex web of matter and energy, with galaxies and galaxy clusters forming a cosmic network. This structure is often described as a cosmic web, with filaments of dark matter and galaxies surrounding vast, empty voids. The largest structures observed are galaxy superclusters, which can span hundreds of millions of light-years. These superclusters are not uniformly distributed, but rather form a pattern that resembles a foam, with clusters and filaments surrounding empty spaces. Two primary theories attempt to explain the formation and evolution of this large-scale structure: the top-down and bottom-up scenarios. The top-down approach suggests that the universe initially consisted of a few massive structures that fragmented into smaller ones over time. In contrast, the bottom-up theory proposes that small structures formed first, which then merged to create larger ones. Current observations and simulations strongly support the bottom-up scenario, where galaxies and galaxy clusters formed from the merger of smaller units. This is consistent with the hierarchical structure observed in the cosmic web. The implications of the large-scale structure are profound. The distribution of galaxies and galaxy clusters provides insights into the nature of dark matter and dark energy, which dominate the universe's mass-energy content. The cosmic web structure also influences the evolution of galaxies, as their interactions and mergers are shaped by their environment. Moreover, the large-scale structure serves as a cosmic laboratory for testing theories of gravity and cosmology. For instance, the observed patterns can help distinguish between different models of dark energy and the accelerated expansion of the universe. Additionally, the structure's evolution over time offers a window into the universe's past and future, providing clues about its ultimate fate. Dark matter, evidence and implications. Dark matter is a mysterious and invisible form of matter that does not emit, absorb, or reflect light, making it undetectable by conventional means. Its existence is inferred through gravitational effects on visible matter, such as stars and galaxies. The evidence for dark matter comes from various astronomical observations, including the rotation curves of galaxies, the gravitational lensing of background radiation by galaxy clusters, and the large-scale structure of the universe. For instance, the rotation curves of spiral galaxies often show that the outer regions rotate at a constant speed, which cannot be explained by the visible matter alone. This suggests the presence of a massive, invisible halo of dark matter surrounding these galaxies. Several theories attempt to explain the nature of dark matter. The most widely accepted hypothesis is that dark matter consists of weakly interacting massive particles, WIMPs, which interact with normal matter through gravity and the weak nuclear force, but not electromagnetically. Another theory proposes that dark matter could be composed of axions, hypothetical particles that are extremely light and interact very weakly with other matter. Alternatively, some scientists suggest that modifications to the laws of gravity, such as modified Newtonian dynamics, could explain the observed phenomena without invoking dark matter. However, these alternative theories have not gained as much traction as the WIMP hypothesis, as they often struggle to explain all the observed data consistently. The implications of dark matter are profound for our understanding of the universe. It plays a crucial role in the formation and evolution of cosmic structures, influencing the distribution of galaxies and galaxy clusters. Without dark matter, the universe would look very different, with fewer large-scale structures and a more uniform distribution of matter. Additionally, dark matter is a key component in the quest to understand the ultimate fate of the universe. Its gravitational effects could determine whether the universe will continue expanding indefinitely, collapse in a big crunch, or reach a state of equilibrium. The study of dark matter also has implications for particle physics, as it could provide insights into new physics beyond the standard model, potentially leading to groundbreaking discoveries. Despite extensive research, dark matter remains one of the biggest mysteries in modern astrophysics. The search for direct evidence of dark matter particles is ongoing, with experiments like the Large Hadron Collider, LHC, and various underground detectors aiming to detect WIMPs or other potential dark matter candidates. Indirect detection methods, such as looking for gamma-ray signatures from dark matter annihilation, are also being pursued. The discovery of dark matter would not only solve a long-standing puzzle, but also open up new avenues for exploring the fundamental nature of the universe. Until then, the enigma of dark matter continues to captivate scientists and fuel their quest for understanding the cosmos. Dark energy, observations, and theories. In the vast expanse of the cosmos, dark energy has emerged as one of the most perplexing and intriguing phenomena. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating, a discovery that led to the widespread acceptance of dark energy as the driving force behind this cosmic acceleration. This acceleration is counterintuitive, as one might expect the gravitational pull of matter to slow down the expansion over time. However, the observed acceleration suggests that roughly 68% of the universe's energy density is composed of dark energy, a form of energy that is uniformly distributed throughout space and exerts a repulsive gravitational effect. Several theories attempt to explain the nature of dark energy. The most straightforward explanation is the cosmological constant, a term introduced by Albert Einstein in his field equations of general relativity. This constant represents a small, positive energy density inherent to space itself. When the universe expands, more space comes into existence, and with it, more of this energy density. This model aligns well with current observations, but it raises profound questions about the fine-tuning of the cosmological constant's value. The observed value is incredibly small compared to theoretical predictions, a discrepancy that has puzzled physicists for decades. An alternative theory posits that dark energy is a dynamic quantity, changing over time. This idea is encapsulated in models of quintessence, where a scalar field permeates the universe, evolving with time and space. Unlike the cosmological constant, quintessence can vary, potentially explaining the observed acceleration without the fine-tuning problem. However, these models introduce new complexities, such as the need for additional fields and interactions, which have not yet been observed. Another intriguing possibility is that dark energy is a manifestation of modifications to the laws of gravity on cosmic scales. These modified gravity theories suggest that our current understanding of gravity may be incomplete, and that dark energy is an artifact of these incomplete theories. The implications of dark energy are profound. If the acceleration continues unabated, the universe may face a Big Rip scenario, where the expansion becomes so rapid that it tears apart galaxies, stars, and even atoms. Conversely, if dark energy is a dynamic quantity, its evolution could lead to different outcomes, such as a big freeze, where the universe expands and cools to a state of maximum entropy. Understanding the true nature of dark energy is crucial for predicting the ultimate fate of the universe. Current and future observations, such as those from the Dark Energy Survey and the Euclid Space Telescope, aim to shed light on this enigmatic component of the cosmos. These efforts will not only deepen our understanding of dark energy, but also provide insights into the fundamental laws governing the universe. The Friedmann Equations. The Friedmann Equations, derived by Alexander Friedmann in the 1920s, are a set of equations in physical cosmology that govern the expansion of space in the context of general relativity. They provide a foundation for the standard Big Bang model of the universe. These equations describe the expansion of the universe in terms of the scale factor, which measures the relative expansion of the universe over time. The first Friedmann equation, often referred to as the Friedmann-Lemaitre equation, relates the Hubble parameter, the density of the universe, and the curvature of space. The second equation describes how the scale factor evolves over time, taking into account the effects of gravity, dark energy, and other forms of energy and matter. Comparing different cosmological theories, the Friedmann equations stand out for their simplicity and elegance. They assume a homogeneous and isotropic universe, which aligns with the cosmological principle. This principle states that the universe looks the same in all directions from any point in space. Alternative theories, such as those involving a non-homogeneous or anisotropic universe, require more complex equations and often lead to predictions that are difficult to test observationally. The Friedmann equations, on the other hand, have been extensively tested and confirmed by observations of the cosmic microwave background radiation, the large-scale structure of the universe, and the acceleration of the universe's expansion. The implications of the Friedmann equations are profound. They predict that the fate of the universe depends on its current density and the presence of dark energy. If the density of the universe is greater than a critical value, the universe will eventually stop expanding and collapse in a big crunch. If the density is less than the critical value, the universe will expand forever, eventually becoming cold and empty. Observations suggest that the universe is very close to the critical density, implying a flat or nearly flat geometry. The discovery of dark energy, which causes the expansion of the universe to accelerate, adds another layer of complexity. This acceleration suggests that the universe will expand forever, but the ultimate fate remains uncertain. In practical terms, the Friedmann equations provide a framework for understanding the large-scale behavior of the universe. They allow cosmologists to make predictions about the age of the universe, the distribution of galaxies, and the nature of dark matter and dark energy. For example, the equations can be used to estimate the age of the universe by extrapolating the current rate of expansion back to the Big Bang. They also help in understanding the formation of large-scale structures, such as galaxy clusters and superclusters. By solving the equations for different initial conditions, cosmologists can explore various scenarios for the evolution of the universe. This flexibility makes the Friedmann equations a powerful tool in modern cosmology. The Friedmann-Lemaitre-Robertson-Walker FLRW metric. The Friedmann-Lemaitre-Robertson-Walker FLRW metric is a solution to Einstein's field equations of general relativity that describes a homogeneous, isotropic universe. This metric is fundamental in modern cosmology, providing a mathematical framework for understanding the large-scale structure and evolution of the universe. It assumes that the universe is uniform on the largest scales, a principle known as the cosmological principle. This assumption allows for significant simplifications, making the metric an invaluable tool for studying the universe's expansion, curvature, and ultimate fate. The FLRW metric incorporates several key parameters that dictate the universe's geometry and dynamics. The scale factor, often denoted as T, describes how the size of the universe changes with time. This factor is crucial for understanding the universe's expansion and the redshift of distant galaxies. The curvature parameter, K, determines the universe's spatial geometry, which can be positive, closed, negative, open, or zero, flat. Observations, particularly of the cosmic microwave background radiation, strongly suggest that the universe is spatially flat, implying that the total energy density of the universe is equal to the critical density. Comparing the FLRW metric with other cosmological models reveals its strengths and limitations. For instance, the steady-state theory, which posits a constant universe with continuous matter creation, is incompatible with the FLRW metric's dynamic scale factor. Inflationary cosmology, on the other hand, aligns well with the FLRW framework, explaining the observed flatness and homogeneity of the universe. The FLRW metric also provides a basis for comparing different models of the universe's fate, such as the Big Freeze, Big Rip, or Big Crunch scenarios. Each of these scenarios corresponds to different values of the cosmological parameters within the FLRW metric. The implications of the FLRW metric are profound and far-reaching. It allows cosmologists to model the universe's expansion history and predict its future evolution. For example, the metric can be used to calculate the age of the universe, the rate of expansion, and the distribution of matter and energy. It also provides a framework for testing cosmological theories against observational data. Recent advancements in observational cosmology, such as the detection of gravitational waves and precise measurements of the cosmic microwave background, have further validated the FLRW metric's predictions. However, the metric's reliance on the cosmological principle means that it may not fully capture the complexities of the universe's structure on smaller scales. Despite this, the FLRW metric remains a cornerstone of modern cosmology, offering deep insights into the shape and fate of the universe. Models of the universe: open, closed, and flat. The universe, in its vastness, can be described by different models that predict its shape and ultimate fate. These models, open, closed, and flat, are based on the geometry of the universe and the amount of matter and energy it contains. Each model offers a unique perspective on how the universe might evolve over time. The open universe model suggests a saddle-like shape, where the universe will expand forever, eventually becoming colder and darker. This model assumes that the density of matter and energy is less than the critical density required to halt expansion. In contrast, the closed universe model envisions a sphere-like shape, where the universe will eventually stop expanding and begin to collapse in on itself, leading to a big crunch. This scenario requires the density of matter and energy to be greater than the critical density. The flat universe model, which aligns with current observations, posits a universe that is geometrically flat, expanding forever but at a rate that slows down over time. This model suggests that the density of matter and energy is very close to the critical density. Comparing these theories reveals their implications for the future of the universe. The open universe model implies an endless expansion, leading to a cold, dilute state where galaxies drift apart and stars burn out. This scenario is often associated with the Big Freeze or heat death, where the universe reaches a state of maximum entropy. The closed universe model, on the other hand, suggests a cyclical pattern, with the universe expanding and then collapsing, potentially leading to a new Big Bang and a new cycle of cosmic evolution. This model is intriguing because it offers the possibility of a recurring universe, although it faces challenges in explaining the initial conditions for each cycle. The flat universe model, supported by observations of the cosmic microwave background radiation, suggests a balanced universe that expands forever but at a decelerating rate. This model is consistent with the presence of dark energy, which is believed to be driving the accelerated expansion of the universe. The implications of these models extend beyond cosmology, influencing our understanding of physics, philosophy, and even theology. The open universe model, with its endless expansion, raises questions about the ultimate fate of life and the possibility of an infinite future. The closed universe model, with its cyclical nature, offers a sense of cosmic recurrence and the potential for an eternal universe. The flat universe model, with its balanced expansion, suggests a universe that is finely tuned, raising questions about the nature of dark energy and the fundamental constants of physics. Each model provides a different lens through which to view the universe, shaping our understanding of its origins, evolution, and ultimate destiny. As observational data continues to refine our understanding of the universe's geometry and composition, the debate over these models will likely evolve, offering new insights into the nature of reality. The critical density and density parameter. The universe's fate hinges on a delicate balance between its expansion and the gravitational pull of its constituent matter and energy. Central to this cosmic tug-of-war is the concept of critical density, a theoretical value that represents the density of matter and energy required for the universe to eventually halt its expansion and recollapse. This value is approximately 10 carat, 29 grams per cubic centimeter, a staggeringly low figure that underscores the vast, empty expanses of the cosmos. The density parameter, denoted by the Greek letter omega, quantifies the ratio of the universe's actual density to this critical density. It's a dimensionless number that offers profound insights into the universe's ultimate destiny. If the density parameter is greater than 1, the universe's density exceeds the critical density, and gravity will eventually overcome the initial expansion, leading to a big crunch. Conversely, if omega is less than 1, the universe's density is insufficient to halt expansion, resulting in a big freeze. In this scenario, galaxies drift apart, stars burn out, and the universe cools to absolute zero. The most intriguing possibility is an omega of exactly 1, a perfectly balanced universe that expands forever, but at an ever-decelerating rate. This is often referred to as the flat or Euclidean universe, where the geometry of space is akin to that of a flat sheet of paper. Observational evidence, particularly from the cosmic microwave background radiation and the distribution of galaxies, strongly suggests that the universe is very close to flat, with omega approximately equal to 1. However, this apparent balance raises profound questions. The critical density is so finely tuned that even a minuscule deviation in the early universe would have led to a vastly different cosmic fate. This fine-tuning has sparked intense debate among cosmologists, with some invoking the anthropic principle, the idea that the universe must be compatible with our existence, to explain the observed value of omega. Others propose more radical theories, such as the existence of a cosmological constant or dark energy, to account for the universe's accelerated expansion. The interplay between critical density and the density parameter also has implications for the nature of dark matter and dark energy, which together constitute approximately 95% of the universe's total energy density. Dark matter, which does not emit or absorb light, exerts a gravitational influence that shapes the large-scale structure of the universe. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. Understanding the precise values of omega for these mysterious components is crucial for unraveling the universe's ultimate fate. Ongoing and future observations, such as those from the Euclid Space Telescope and the Large Synoptic Survey Telescope, aim to refine our measurements of the density parameter and shed light on the enigmatic nature of dark matter and dark energy. The age of the universe. Determining the age of the universe is a complex endeavor that involves a deep understanding of cosmology, physics, and astronomy. Current estimates place the universe at approximately 13.8 billion years old, a figure derived from the most widely accepted cosmological model, the lambda CDM model. This model incorporates the cosmological constant, lambda, and cold dark matter, CDM, to explain the observed acceleration of the universe's expansion and the distribution of matter. The age is calculated by measuring the rate of expansion, known as the Hubble constant, and extrapolating back to the beginning of time, the Big Bang. However, this figure is not without its controversies and uncertainties. One of the primary methods for estimating the universe's age involves studying the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang. Satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided detailed maps of the CMB, allowing scientists to infer the age of the universe with remarkable precision. These measurements rely on the assumption that the universe is isotropic and homogeneous on large scales, meaning it looks the same in all directions and has a uniform distribution of matter and energy. While this assumption holds for the most part, there are always nuances and potential deviations that could affect the accuracy of these estimates. Alternative theories and models challenge the conventional understanding of the universe's age. For instance, some theories propose that the universe may have gone through phases of rapid expansion or contraction, which could significantly alter the calculated age. Additionally, the presence of dark energy, a mysterious force driving the acceleration of the universe's expansion, adds another layer of complexity. Different models of dark energy can lead to varying estimates of the universe's age, highlighting the need for more precise measurements and a deeper understanding of its fundamental properties. The implications of these theories are profound, as they could reshape our understanding of the universe's origin, evolution, and ultimate fate. The age of the universe also has practical implications for our understanding of stellar and galactic evolution. Older stars and galaxies provide a window into the early universe, allowing scientists to test and refine their models. For example, the discovery of extremely old stars in the Milky Way, estimated to be nearly as old as the universe itself, offers valuable insights into the conditions and processes that prevailed in the early universe. These stars, often referred to as Methuselah stars, challenge our understanding of stellar evolution and the formation of the first generation of stars. By studying these ancient celestial objects, scientists can gain a better understanding of the universe's age and the processes that have shaped its evolution over billions of years. Nucleosynthesis and the early universe. The universe, in its earliest moments, was a hot, dense place, vastly different from the one we observe today. Nucleosynthesis, the process by which atomic nuclei are formed, began just seconds after the Big Bang. Initially, only the lightest elements, such as hydrogen and helium, could form. This primordial nucleosynthesis was constrained by the rapid expansion and cooling of the universe. The abundance of these elements today offers a window into the conditions of the early universe. For instance, the ratio of hydrogen to helium isotopes provides evidence supporting the Big Bang model. However, heavier elements, like carbon and oxygen, had to wait until stars formed and began fusing lighter elements in their cores. Two primary theories explain the formation of these heavier elements: the R process and the S process. The S process, or slow neutron capture, occurs in the late stages of a star's life, particularly in asymptotic giant branch stars. It involves the gradual capture of neutrons by seed nuclei, building up heavier elements over time. In contrast, the R process, or rapid neutron capture, is thought to occur in more violent events, such as neutron star mergers or supernovae. Here, neutrons are captured much more rapidly, leading to the formation of very heavy elements. The distinction between these processes is crucial for understanding the chemical evolution of the universe. For example, gold and uranium are primarily products of the R process, while elements like strontium and barium are mainly formed through the S process. The implications of these theories are profound. The relative abundances of elements in the universe can be used to trace its history and evolution. For instance, the presence of certain isotopes can indicate the occurrence of specific astrophysical events. Moreover, the study of nucleosynthesis helps us understand the life cycles of stars and the dynamics of galactic evolution. It also raises questions about the initial conditions of the universe and the fundamental forces that govern it. For example, the fine-tuning of the strong nuclear force is crucial for the formation of elements heavier than hydrogen. A slight variation in this force could have led to a universe with vastly different chemistry, and perhaps no life as we know it. Recent observations and simulations have provided valuable insights into these processes. For example, the detection of gravitational waves from neutron star mergers has offered direct evidence for the R process. Meanwhile, studies of stellar spectra and meteoritic material have shed light on the S process. These advancements have not only confirmed existing theories, but also opened up new avenues for exploration. They have also highlighted the interconnectedness of various astrophysical phenomena. For instance, the study of nucleosynthesis is intrinsically linked to the understanding of dark matter and dark energy, which dominate the energy density of the universe. Thus, the exploration of the early universe and its nucleosynthesis is not just a journey into the past, but also a key to unlocking the mysteries of the cosmos. Inflationary theory. The universe, in its vast expanse, has long been a subject of fascination and inquiry. One of the most compelling theories attempting to explain its shape and fate is the inflationary theory. This theory posits that the universe underwent a period of exponential expansion, known as cosmic inflation, in the moments following the Big Bang. This rapid expansion is thought to have smoothed out the universe and made it largely uniform, a characteristic that is evident in the cosmic microwave background radiation, the afterglow of the Big Bang. The theory also suggests that quantum fluctuations during this inflationary period could have seeded the large-scale structure of the universe, leading to the formation of galaxies and galaxy clusters. Inflationary theory stands in contrast to other cosmological models, such as the steady-state theory, which proposes that the universe has always existed in the same state, with matter continuously created to maintain a constant density. Unlike the steady-state theory, inflationary theory provides a mechanism for the observed acceleration of the universe's expansion, a phenomenon attributed to dark energy. This distinction is crucial as it aligns with observations of distant supernovae, which appear dimmer than expected, indicating an accelerating universe. Additionally, inflationary theory offers explanations for the flatness problem and the horizon problem, which are challenges to the standard Big Bang model. The implications of inflationary theory are profound. If the universe underwent a period of rapid inflation, it suggests that the visible universe is just a tiny fraction of a much larger, perhaps infinite, multiverse. This idea opens up the possibility of other universes with different physical laws and constants. Moreover, the theory has testable predictions, such as the specific pattern of temperature fluctuations in the cosmic microwave background. Observations by satellites like WMAP and Planck have provided strong evidence supporting these predictions, bolstering the credibility of inflationary theory. However, it's not without its critics and alternative theories, such as the ekpyrotic universe model, which proposes that the universe was formed from the collision of higher-dimensional objects. In practical terms, understanding the shape and fate of the universe has implications for our understanding of fundamental physics. It drives research into dark matter and dark energy, which together make up about 95% of the universe's energy density. It also influences our understanding of the laws of physics, particularly at the quantum scale. For instance, the theory of cosmic inflation is deeply tied to quantum field theory, which describes the behavior of fundamental forces and particles. As such, advancements in cosmology often go hand in hand with advancements in particle physics. The quest to understand the universe's shape and fate is not just a philosophical endeavor, but a scientific one with far-reaching implications for our understanding of reality itself. Quantum fluctuations and cosmic structure. Quantum fluctuations, tiny variations in energy that occur spontaneously in empty space, have profound implications for the large-scale structure of the universe. These fluctuations, predicted by quantum field theory, are not merely mathematical abstractions, but have observable consequences. In the early universe, quantum fluctuations in the density of matter provided the seeds for the cosmic structures we see today. As the universe expanded, regions with slightly higher density attracted more matter through gravity, eventually leading to the formation of galaxies, stars, and other cosmic structures. This process, known as structure formation, is a cornerstone of modern cosmology. The theory of cosmic inflation, which posits a period of exponential expansion in the early universe, provides a framework for understanding how quantum fluctuations could have given rise to the large-scale structure we observe. During inflation, quantum fluctuations were stretched to macroscopic scales, creating density variations that seeded the formation of cosmic structures. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, provides a snapshot of these early density fluctuations. Measurements of the CMB by satellites like WMAP and Planck have confirmed the predictions of inflationary theory, showing a pattern of temperature variations that matches the expected distribution of quantum fluctuations. However, not all theories agree on the details of how quantum fluctuations influence cosmic structure. Some alternative models, such as ekpyrotic universe or cyclic models, propose different mechanisms for structure formation. In these scenarios, collisions between branes or cyclic cosmic events could generate density fluctuations without the need for an inflationary phase. These theories offer different predictions for the statistical properties of the CMB and the distribution of matter in the universe. Observational data, particularly from upcoming surveys like the Large Synoptic Survey Telescope, LSST, and the Euclid mission, will be crucial in distinguishing between these competing theories. The implications of quantum fluctuations on cosmic structure extend beyond the formation of galaxies and stars. They also influence the overall shape and fate of the universe. The distribution of matter affects the rate of cosmic expansion, which in turn determines whether the universe will expand forever, collapse in a big crunch, or reach a state of equilibrium. Understanding the role of quantum fluctuations in structure formation is therefore essential for predicting the long-term evolution of the cosmos. Moreover, these fluctuations provide a window into the fundamental physics of the early universe, offering insights into the nature of quantum gravity and the unification of the fundamental forces. The shape of the universe, curvature, and topology. The universe's shape is a complex interplay of curvature and topology, two fundamental aspects that determine its overall geometry. Curvature refers to how space deviates from being flat, while topology deals with the universe's large-scale structure and connectivity. These concepts are not just abstract ideas. They have profound implications for our understanding of the cosmos. For instance, the curvature of the universe influences how light travels through space, affecting our observations of distant galaxies and the cosmic microwave background radiation. Meanwhile, the topology of the universe could reveal whether it is infinite or finite, and whether it has any unusual connections or holes. Different theories propose various shapes for the universe, each with its own set of implications. A positively curved universe, often likened to the surface of a sphere, would imply a closed and finite universe that eventually curves back on itself. In such a scenario, if you were to travel far enough in one direction, you might eventually return to your starting point. Conversely, a negatively curved universe, similar to a saddle shape, would suggest an open and infinite universe that expands forever. A flat universe, on the other hand, would mean that the geometry of space adheres to Euclidean principles, with parallel lines never meeting and the sum of angles in a triangle always equaling 180 degrees. The topology of the universe adds another layer of complexity. Even if the universe is positively curved, it could have a complex topology, meaning it might have multiple connected regions or unusual shapes. For example, a universe with a toroidal topology would resemble a donut, where traveling in one direction would bring you back to your starting point, but in a different orientation. These topological features could leave subtle imprints on the cosmic microwave background radiation, providing clues about the universe's true shape. Scientists analyze data from satellites like the Planck satellite to search for these patterns, hoping to unravel the mysteries of the universe's topology. Understanding the shape of the universe is not just an academic exercise. It has practical implications for our understanding of cosmology. The curvature and topology of the universe influence its ultimate fate. A positively curved universe would eventually stop expanding and collapse in a big crunch, while a negatively curved or flat universe would continue expanding forever. The topology could also affect the distribution of matter and the formation of structures like galaxies and galaxy clusters. By studying the shape of the universe, scientists hope to gain insights into its origins, evolution, and ultimate destiny. This quest to understand the cosmos is ongoing, with new observations and theoretical developments continually shaping our understanding of the universe's true nature. The accelerating universe and dark energy. The universe, it seems, is not just expanding but accelerating in its expansion. This discovery, which earned the 2011 Nobel Prize in Physics, was a game-changer in cosmology. The acceleration is attributed to a mysterious force, or energy, known as dark energy. It's a concept that challenges our understanding of the cosmos and has sparked intense debate and research. Dark energy is thought to make up about 68% of the universe's total energy density. Its existence is inferred from observations of the cosmic microwave background, the large-scale structure of the universe, and the acceleration of distant supernovae. Yet, its nature remains one of the most profound mysteries in physics. One leading theory is that dark energy is a property of space itself, a kind of energy associated with the vacuum. This is often referred to as the cosmological constant, a concept first introduced by Albert Einstein. However, the value of this constant, as predicted by quantum field theory, is vastly different from the value observed in cosmological measurements. This discrepancy is a significant puzzle. Alternative theories abound. Some scientists propose that dark energy is a dynamic quantity, changing over time, rather than a constant. This could be due to a new kind of dynamical field, often referred to as quintessence. Others suggest that the acceleration is not due to dark energy at all, but rather a breakdown of our understanding of gravity on cosmological scales. Modified gravity theories, such as FLRW or the DGP model, attempt to explain the acceleration without invoking dark energy. Each of these theories has its own implications for the ultimate fate of the universe. If dark energy is indeed a cosmological constant, the universe will continue to expand at an accelerating rate, leading to a big freeze, where galaxies become isolated islands in an ever-expanding cosmos. If dark energy is dynamic, the future of the universe could be even more uncertain, with possibilities ranging from a big rip to a cyclic universe. The implications of these theories are profound, touching on the very nature of space, time, and existence itself. The cosmological constant. The cosmological constant, often denoted by the Greek letter lambda, is a term that represents the energy density of space itself. It was first introduced by Albert Einstein in his field equations of general relativity as a means to achieve a static universe, a concept he later abandoned upon the discovery of the universe's expansion. However, the cosmological constant has seen a resurgence in modern cosmology, playing a pivotal role in our understanding of the universe's acceleration. In the late 20th century, observations of distant supernovae revealed that the universe's expansion is not slowing down due to gravity, as one might expect, but is instead accelerating. This acceleration is attributed to dark energy, a mysterious force that makes up approximately 68% of the universe's total energy density. The cosmological constant is one of the leading candidates to explain dark energy. It posits that the vacuum of space is not empty, but filled with a constant energy density, which exerts a repulsive force that counteracts gravity and drives the accelerated expansion. Comparing theories, the cosmological constant is often pitted against other models of dark energy, such as quintessence. Unlike the cosmological constant, which is a fixed value, quintessence suggests that dark energy is a dynamic field that changes over time. This could mean that the acceleration of the universe's expansion might not be constant, but could vary. However, current observations do not provide strong evidence for this variability, making the cosmological constant a more parsimonious explanation. That said, the cosmological constant is not without its problems. The observed value of the cosmological constant is incredibly small compared to theoretical predictions, a discrepancy known as the cosmological constant problem. This fine-tuning issue has led some physicists to explore alternative theories, but none have yet gained widespread acceptance. The implications of the cosmological constant are profound. If the cosmological constant is indeed the explanation for dark energy, then the universe's fate is one of eternal expansion and cooling, often referred to as the Big Freeze or heat death. Galaxies will drift apart, stars will burn out, and the universe will become increasingly cold and empty. This scenario is bleak, but it is a direct consequence of the cosmological constant's repulsive force. Moreover, the cosmological constant's small but non-zero value has led to speculation about the anthropic principle, which suggests that the universe's constants are fine-tuned to allow for our existence. This is a controversial idea, but it highlights the deep connections between fundamental physics and the large-scale structure of the universe. Quintessence and dark energy models. The universe's expansion isn't just happening, it's accelerating. This puzzling observation has led scientists to propose various models to explain this phenomenon, with quintessence and dark energy being two prominent contenders. Dark energy, a mysterious form of energy thought to permeate all of space, is the leading explanation for this cosmic acceleration. It's often associated with Einstein's cosmological constant, a fudge factor he initially introduced to achieve a static universe, which he later discarded. However, the cosmological constant model has its issues, like the fine-tuning problem and the cosmological constant problem, which has sparked interest in alternative models like quintessence. Quintessence, a dynamic form of dark energy, is a hypothetical form of energy that changes over time, unlike the constant dark energy. It's a scalar field that evolves with time, affecting the expansion rate of the universe. This model offers a solution to some of the problems faced by the cosmological constant model. For instance, it can explain why the expansion of the universe is accelerating without requiring an extremely fine-tuned cosmological constant. Moreover, quintessence can also account for the possibility that the dark energy density might change in the future, leading to different scenarios for the ultimate fate of the universe. Comparing these models reveals their strengths and weaknesses. The cosmological constant model is simpler and has fewer free parameters, making it more predictable. However, it struggles with the aforementioned fine-tuning problems. On the other hand, quintessence models are more complex and can provide a more nuanced explanation for the universe's acceleration. They can also accommodate a wider range of cosmological observations. Yet, they require more assumptions and lack the same level of predictive power as the cosmological constant model. The implications of these models are profound. If dark energy is indeed a cosmological constant, the universe might continue to expand indefinitely, leading to a Big Freeze scenario where galaxies become isolated islands in an ever-expanding cosmos. Conversely, if quintessence is the culprit, the fate of the universe could be more complex. The dark energy density could decrease, leading to a Big Crunch scenario, or it could even become repulsive, causing the universe to expand at an ever-increasing rate. These models not only shape our understanding of the universe's fate, but also guide our search for new physics beyond the standard model. The future of the universe, heat death, or Big Rip. The universe, in its vast and mysterious expanse, is subject to various theoretical fates, two of which stand out due to their profound implications: heat death and the Big Rip. These scenarios emerge from our current understanding of cosmology, particularly the behavior of dark energy and the second law of thermodynamics. Heat death, a concept rooted in the 19th century studies of thermodynamics, envisions a future where the universe reaches a state of maximum entropy. In this scenario, all energy is evenly distributed, rendering it unavailable to perform work. The cosmos would become a uniform, lifeless expanse, devoid of the energy gradients necessary for any form of activity. This outcome is often associated with a universe that continues to expand, but at a rate that eventually slows down due to the gravitational attraction of matter. Conversely, the Big Rip posits a more dramatic end. This theory is predicated on the accelerating expansion of the universe, driven by dark energy. If dark energy's repulsive force continues to increase, it could eventually overcome all other forces, including gravity. In this scenario, the expansion would become so rapid that it would tear apart everything from galaxy clusters to individual atoms. The Big Rip would culminate in a singularity where the fabric of space-time itself is torn apart. This outcome is particularly unsettling, as it suggests a violent end to all structures in the universe, including the fundamental particles that make up matter. The distinction between these two fates hinges on the nature of dark energy and its behavior over cosmic timescales. The implications of these theories are profound and far-reaching. Heat death implies a gradual, almost inevitable decline into a state of thermodynamic equilibrium. This scenario suggests that the universe will eventually become a cold, dark, and lifeless place, where no energy is available to sustain any form of life or activity. It is a bleak but somewhat serene vision of the end, where the universe simply winds down like a clock. In contrast, the Big Rip presents a more chaotic and violent end. It suggests that the universe will be torn apart in a rapid and catastrophic manner, with all structures, from galaxies to atoms, being ripped apart by the ever-increasing expansion. This scenario is more alarming as it implies that even the fundamental building blocks of the universe will be destroyed. The choice between these two fates is not merely academic. It has significant implications for our understanding of the universe and our place within it. If the universe is headed towards heat death, it suggests that the laws of thermodynamics will ultimately prevail and all energy will be evenly distributed. This outcome would mean that the universe will eventually reach a state of maximum entropy, where no further work can be done. In contrast, if the Big Rip is the ultimate fate, it suggests that dark energy will continue to dominate the universe, leading to an ever-accelerating expansion that will ultimately tear everything apart. This scenario would imply that the universe is fundamentally unstable and that all structures, no matter how large or small, are ultimately doomed to be destroyed. The ultimate fate of stars and galaxies. Stars and galaxies, the building blocks of the universe, have lifespans and fates that are intricately tied to the laws of physics and the initial conditions of the cosmos. Our understanding of these fates is shaped by observations and theoretical models, which often lead to competing theories. The ultimate fate of stars is primarily determined by their mass. Low to medium mass stars, like our Sun, will exhaust their nuclear fuel and shed their outer layers, forming planetary nebulae and leaving behind dense, Earth-sized cores called white dwarfs. These white dwarfs will slowly cool and fade over trillions of years. High-mass stars, on the other hand, end their lives in spectacular supernova explosions, leaving behind either neutron stars or black holes, depending on the mass of the remaining core. The fate of galaxies is more complex and depends on factors such as their interactions with other galaxies and the nature of dark matter and dark energy. One prominent theory about the fate of galaxies is the heat death or Big Freeze scenario, which posits that the universe will continue to expand indefinitely. In this scenario, galaxies will become isolated islands in an ever-cold and ever-expanding cosmos. Stars will burn out, and without new stars forming, galaxies will grow darker and darker. The Big Crunch is another theory, suggesting that the expansion of the universe will eventually reverse, leading to a collapse back into a hot, dense state. However, current observations of the accelerating expansion of the universe, attributed to dark energy, make this scenario less likely. Another intriguing possibility is the Big Rip, where the expansion of the universe becomes so rapid that it tears apart galaxies, stars, and even atoms. The implications of these theories are profound, as they shape our understanding of the ultimate fate of all structures in the universe. The study of the ultimate fate of stars and galaxies is not just an academic exercise. It has practical implications for our understanding of the universe and our place in it. For instance, the fate of stars is crucial for the recycling of matter in the universe. Supernovae, in particular, are responsible for dispersing heavy elements, which are the building blocks of planets and life as we know it. The fate of galaxies, on the other hand, influences the large-scale structure of the universe and the distribution of matter. Understanding these fates can also provide insights into the nature of dark matter and dark energy, which remain some of the biggest mysteries in cosmology. Moreover, the study of these fates can help us understand the long-term prospects of our own Milky Way galaxy and the local group of galaxies to which it belongs. The holographic principle and the universe's information content. The holographic principle is a fascinating concept in theoretical physics that suggests the entire universe could be encoded on a two-dimensional surface, much like a hologram. This principle emerged from the study of black holes and string theory, proposing that the information contained within a volume of space can be described by the information on its boundary. It's a radical departure from classical physics, which assumes that information is distributed throughout a three-dimensional space. The principle implies that our 3D universe might be a projection of information stored on a 2D surface, potentially at the edge of the universe or within each fundamental particle. Comparing this to other theories, the holographic principle offers a stark contrast to the traditional Big Bang cosmology, which describes the universe as a dynamic, evolving entity. While Big Bang theory focuses on the expansion and cooling of the universe, the holographic principle shifts attention to the information content and its encoding. This shift has profound implications for understanding the universe's fate. If the holographic principle holds true, the universe's ultimate fate might be tied to the stability and evolution of this encoded information, rather than the traditional metrics of heat death or big crunch scenarios. The implications of the holographic principle are vast and thought-provoking. It suggests that the universe's complexity and structure could be an illusion, a projection from a lower-dimensional reality. This idea challenges our perceptions of space, time, and reality itself. Moreover, it opens up new avenues for understanding quantum gravity, the unification of quantum mechanics, and general relativity. However, the principle is still speculative and lacks direct experimental evidence. Scientists are exploring ways to test it, such as through observations of cosmic microwave background radiation or quantum gravity experiments. Until then, the holographic principle remains a compelling theoretical framework that pushes the boundaries of our understanding. In practical terms, the holographic principle could revolutionize our approach to information theory and quantum computing. If the universe is indeed a hologram, it might imply that information processing is fundamental to the fabric of reality. This could lead to breakthroughs in quantum computing, where information is manipulated at the most fundamental levels. Additionally, it might provide insights into the nature of consciousness and perception, as our experience of reality could be a decoded projection of underlying information. While these ideas are speculative, they highlight the potential impact of the holographic principle on various scientific and philosophical domains. Multiverse theories and cosmology. The cosmos, in its vast and enigmatic expanse, has long captivated human curiosity, leading to the development of various cosmological theories. Among these, multiverse theories have gained significant traction, offering intriguing perspectives on the shape and fate of the universe. These theories suggest that our universe might be just one among countless others, each with its own set of fields and interactions. The most prominent among these is the inflationary multiverse, which posits that our universe underwent a rapid expansion phase known as inflation, leading to the formation of bubble universes with diverse properties. Another compelling theory is the string theory landscape, which proposes a vast number of possible universes, each corresponding to different solutions of string theory. These theories not only challenge our understanding of cosmology, but also have profound implications for the nature of reality itself. Comparing these theories reveals both similarities and differences. The inflationary multiverse and the string theory landscape share the idea of a multitude of universes, each with distinct physical laws. However, they differ in their underlying mechanisms. Inflationary multiverse theories focus on the dynamics of cosmic inflation, while string theory landscape theories emphasize the mathematical solutions of string theory. Despite these differences, both theories suggest that our universe is part of a much larger, perhaps infinite, ensemble. This perspective shifts the focus from a single, unique universe to a vast, diverse multiverse, altering our understanding of cosmology and the fundamental constants of nature. The implications of multiverse theories are far-reaching. If true, they could explain the fine-tuning of our universe's constants, suggesting that we observe a universe compatible with our existence. This idea, known as the anthropic principle, posits that the properties of our universe are not accidental, but are instead a result of our presence as observers. Multiverse theories also challenge the notion of a single, unified theory of everything, as they imply that different universes might operate under different physical laws. This has significant implications for theoretical physics, as it suggests that a comprehensive understanding of the cosmos may require a framework that encompasses multiple, diverse universes. Moreover, these theories raise profound philosophical questions about the nature of reality, the existence of other forms of life, and the ultimate fate of our universe. Anthropic principle and fine-tuning. The universe, with its vast expanse and intricate structures, has long captivated human curiosity. Two concepts that have emerged in the quest to understand its shape and fate are the anthropic principle and the notion of fine-tuning. These ideas intersect in fascinating ways, offering insights into why the universe appears as it does and what this means for its ultimate destiny. The anthropic principle posits that the universe must be compatible with the existence of intelligent life. This isn't a statement about the inevitability of life, but rather an observation that our existence influences how we perceive the universe. There are two main versions of this principle: the weak anthropic principle, which states that we should expect to find ourselves in a region of the universe that is compatible with our existence, and the strong anthropic principle, which suggests that the universe must have properties that allow for the development of intelligent life at some stage. The latter implies a kind of design or purpose, which can be controversial. Critics argue that it introduces a teleological element that is not necessarily supported by empirical evidence. Proponents, however, see it as a way to reconcile the fine-tuned nature of the universe with our presence in it. Fine-tuning, on the other hand, refers to the observation that the fundamental constants of nature, such as the gravitational constant, the fine structure constant, and the cosmological constant, seem to be precisely tuned to allow for the existence of life. Even slight variations in these constants could render the universe inhospitable to life as we know it. For example, if the strong nuclear force were slightly stronger, stars would burn out too quickly for life to develop. If it were weaker, the fusion processes that power stars would not occur. This fine-tuning has led some to argue that the universe is not just a product of chance, but perhaps the result of a multiverse, where countless universes exist with different physical constants, and we just happen to be in one that is life-permitting. This multiverse hypothesis is a topic of ongoing debate and research in cosmology and theoretical physics. The implications of these ideas are profound. If the universe is indeed fine-tuned, it raises questions about the nature of reality and our place within it. Some interpret this fine-tuning as evidence for a form of intelligent design, while others see it as a natural outcome of a vast multiverse. The anthropic principle, in turn, suggests that our observations of the universe are inherently biased by our existence. This means that any conclusions we draw about the universe's shape and fate must take into account the fact that we are here to observe them. For instance, the fact that the universe appears to be expanding at an accelerating rate, as evidenced by observations of distant supernovae, might be a feature that allows for the long-term existence of life. Understanding these concepts helps us grapple with the big questions about the universe's ultimate fate, whether it will expand forever, collapse in a big crunch, or something in between. Philosophical implications of cosmological discoveries. The universe, with its vast expanse and mysterious nature, has long been a subject of both scientific inquiry and philosophical contemplation. Recent cosmological discoveries have significantly shaped our understanding of the universe's shape and fate, prompting profound philosophical implications. The prevailing cosmological model, the lambda cold dark matter (lambda-CDM) model, suggests that the universe is flat or very close to flat, with a geometry that aligns with the observations of the cosmic microwave background radiation. This model also posits that the universe will continue to expand indefinitely, driven by dark energy, leading to a big freeze scenario where galaxies move away from each other, and the universe becomes increasingly cold and empty. Comparing this to alternative theories, such as the cyclic model or the Big Rip scenario, reveals differing implications. The cyclic model proposes that the universe undergoes repeated cycles of expansion and contraction, offering a philosophical perspective that aligns with ideas of eternity and rebirth. In contrast, the Big Rip scenario suggests that the expansion of the universe will eventually become so rapid that it tears apart all structures, including galaxies, stars, and even atoms. This bleak fate raises questions about the ultimate meaning and purpose of existence within a universe destined for such an end. The lambda-CDM model, with its infinite expansion, presents a more gradual but equally profound challenge to traditional notions of cosmic destiny. Philosophically, these discoveries compel us to reconsider our place in the universe. The idea of an ever-expanding, increasingly isolated cosmos challenges anthropocentric views and prompts a re-evaluation of human significance. If the universe is destined for a cold, dark fate, what does that say about our existence? Some philosophers argue that this perspective can be liberating, encouraging a focus on the present and the here and now. Others see it as a call to action, urging us to cherish and protect the beauty and complexity of the cosmos while we can. The philosophical implications of these cosmological discoveries are vast and varied, touching on themes of meaning, purpose, and our connection to the broader universe. Open questions and future directions in cosmology. The universe, in its vast and mysterious expanse, continues to pose more questions than answers. One of the most pressing open questions in cosmology is the precise shape of the universe. Current observations suggest that the universe is flat, with a Euclidean geometry, but this conclusion is based on measurements with a certain degree of uncertainty. If the universe is indeed flat, it implies that the total energy density of the universe is perfectly balanced between matter and dark energy, a notion that is both elegant and unsettling in its precision. Alternatively, the universe could be closed, like a sphere, or open, like a saddle, each possibility carrying profound implications for its ultimate fate. A closed universe would eventually collapse in a big crunch, while an open universe would expand forever, growing colder and darker. Another intriguing question revolves around the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Current theories suggest that dark energy could be a property of space itself, a cosmological constant, as Einstein once proposed. However, the observed value of dark energy is incredibly small compared to theoretical predictions, a discrepancy known as the cosmological constant problem. Alternative theories propose that dark energy is a dynamic field, evolving over time, or even that it is an artifact of our incomplete understanding of gravity. Each of these possibilities paints a different picture of the universe's future, from a big rip, where galaxies and even atoms are torn apart, to a big freeze, where the universe expands into a cold, dilute state. The origin and nature of dark matter also remain open questions. Unlike dark energy, dark matter interacts gravitationally, shaping the large-scale structure of the universe. Yet, its composition is unknown. Leading candidates include weakly interacting massive particles, WIMPs, and axions, hypothetical particles that have evaded detection so far. The nature of dark matter could hold clues about the universe's early moments and its eventual fate. For instance, if dark matter interacts with itself, it could form complex structures, altering the universe's evolution. Conversely, if it remains inert, it could simply dilute as the universe expands, leaving behind a cold, dark cosmos. Looking ahead, future directions in cosmology aim to address these open questions with advanced technologies and innovative theories. Upcoming surveys, like the Euclid mission and the Large Synoptic Survey Telescope, LSST, promise to map the universe's structure with unprecedented precision, shedding light on dark energy and dark matter. Meanwhile, experiments like the Large Hadron Collider, LHC, and planned dark matter detectors could directly probe the nature of these elusive components. Theoretically, efforts to unify quantum mechanics and general relativity, such as string theory and loop quantum gravity, could provide a deeper understanding of the universe's fundamental nature. Each of these avenues offers a glimpse into the future of cosmology, a future where the universe's shape and fate may finally be revealed. As we wrap up our journey through the cosmos, let's recap the key points we've explored. We've delved into the three main theories about the shape and fate of our universe: the Big Crunch, the Big Freeze, and the Big Rip. Each theory presents a unique perspective, from a universe that collapses in on itself to one that expands indefinitely, growing colder and darker, or one that is torn apart by dark energy. We've seen how these theories are not just abstract ideas, but have profound implications for our understanding of existence. They shape our view of time, space, and everything in between. The Big Crunch suggests a cyclical universe. The Big Freeze points to an inevitable heat death, and the Big Rip implies a future where even the fabric of space-time is torn asunder. So what does this mean for us? Well, it's a reminder of how much we still don't know. The universe is vast and mysterious, and our quest to understand it is far from over. Whether you're a scientist, a student, or just someone with a curiosity about the cosmos, there's always more to explore. As we continue this journey, we invite you to join us for our next video, where we'll dive into the mysteries of dark matter and dark energy. These invisible forces make up most of our universe, yet we know so little about them. What are they? How do they shape our cosmos? Stay tuned to find out. In the meantime, we'd love to hear your thoughts. Which theory about the fate of the universe resonates with you the most? Do you have any questions or insights to share? Drop them in the comments below. Let's keep the conversation going and the curiosity alive. Until next time, keep looking up and wondering. The universe is waiting.